Okay, let us move on with our chapter about solid-state electrolytes. I told you in the last class that defects are very important for the ion conductivity in solid-state electrolytes, and we have discussed two types of point defects. These were the Schottky defects and the Frankel defects. So we said that when we have a Schottky defect, that an ion pair is missing within a crystal, while when we have a Frankel defect, then one ion, mostly a cation, is dislocated from its equilibrium site to a so-called interstitial site where it has a higher energy. So I also said that Frankel defects mostly occur for cations, rarely for anions, and that is because cations are typically smaller than anions, so they can be delocated to an interstitial site more easily. However, there's one exception, and that is what I mentioned at the very end of the class. Frankel types can occur pretty frequently for the fluoride structure type. So let us look at this more closely and see why the fluoride structure type is an exception. So we can most easily understand this exception when you view the fluoride crystal structure in the fluoride B cell. Okay, the fluoride B cell is depicted here again, and the fluoride B cell has the advantage that it shows clearly that the fluoride structure can be considered to be a defect cesium chloride structure. Okay, so we see here that the calcium ions are surrounded by the fluorines in a cubic fashion. Okay, but only 50% of these cubes are occupied by calcium ions. Okay, you see this here more clearly. Okay, so we have here these cubes and these cubes and this cube and this cube and this cube here, among other cubes, and these cubes represent cubes that have us body-centered with the calcium ion. Okay, whereas there are neighbored cubes here, for instance, here, here, and here, which are not centered. So there's no calcium ion. So there's no calcium ion in it. Okay. So now, because of that, a fluoride ion can fairly easily move from a corner of this cube through such an empty cube to another corner of this cube. Okay, or it can simply reside inside of such a cube, whereby the interior of this empty cube would be considered to be an interstitial site. Okay, and you can also see that this obviously can occur with a low activation barrier. There's no small space through which the fluoride ion would need to squeeze through in order to go to this interstitial site. So this is the explanation why Frankel anionic Frankel defects are common in the fluoride structure, whereas anionic Frankel defects are otherwise not very common. All right, so now through which mechanisms can the ion move in Schottky defects and Frankel defects? Let us first look at the Schottky defects. So here you have an exert of the sodium chloride crystal structure that contains a Frankel defect. Okay, so in this exert of the sodium chloride crystal structure, the sodium ions occupy 50% of the corners, and the chloride ions occupy the other 50% of this corner, but one sodium ion is missing. Okay, of course, there must be also a chloride ion missing somewhere else in that crystal, but this is not shown here. All right. So now, in order to ion conductivity to occur, a sodium ion must migrate from one side to a vacancy. Okay, and it will migrate through the path of lowest resistance. Okay, so therefore it will actually squeeze through the space, okay, inside of that cube. Okay, so now that that space inside of the cube represents also an interstitial site, and it's actually smaller than the radius of the sodium plus ion. So the radius of the sodium plus ion is 95 picometers. So the space inside of this cube here is only 59 picometers. Okay, so therefore the sodium ion must be squeezed together in order to move through this interstitial site. For that reason, this interstitial site represents, well, a higher energy site. Okay, so overall, our sodium ion moves through that interstitial site, okay, to which represents a transition state to another vacancy, okay, which has a lower energy value again. Okay, so this is the mechanism of ion migration for Schottky defects. Now, what about the Franco defects? For the Franco defects, actually two mechanisms are known. One is called the direct interstitial jump, and the other is called the interstitial C mechanism. So these two mechanisms are here illustrated for the example of sodium chloride, which has predominantly Franco defects. So in the direct interstitial jump, a sodium ion, which is on an interstitial site, moves directly to another interstitial site. Okay, the silver chloride structure has also the sodium chloride structure, and you see here two cubes which are part of the unit cell of the sodium chloride, and you see that a sodium ion, a silver ion that sits on an interstitial site can actually squeeze itself through this square window here to move to another interstitial site. So that's called the direct interstitial jump. So the other possibility is that the silver ion knocks off other silver ion which sits on an equilibrium site. Thereby, the first silver ion moves to the equilibrium site, shown here, and the second silver ion moves to a neighbored interstitial site. So this is called the interstitial C mechanism. So both mechanisms can occur depending on the compound. Either the interstitial C mechanism can be dominant, or the direct interstitial jump can be dominant. In the case of the silver chloride, it's actually the interstitial mechanism which occurs more often than the direct interstitial jump. All right, so thus far we have only discussed so-called intrinsic defects. That means defects that are introduced into a pure crystal in the form of, well, ion pairs being missing or ions being dislocated to an interstitial site. However, in addition to these intrinsic defects, we can also have so-called extrinsic defects. So these extrinsic defects, they can be introduced through impurities in the crystal, in particular aliovalent impurities. Okay, and aliovalent means that we have an ion present which has a different charge than the ion, the regular ions in our crystal. So, for instance, we can introduce a manganese chloride impurities into a sodium chloride crystal. Okay, so that means now that manganese substitutes some of the sodium ions in the sodium crystal. Okay, now the manganese has a 2+ charge, while the sodium plus has only 1+ charge. So for that reason, we now need many chloride ions. Okay, and therefore additional some chloride ions in the crystal structure are missing. Okay, creating vacancies. Okay, so overall we will have basically the following composition here. We have the composition Na1 minus 2x, okay, MnX, whereby Mn is just the X just stands for the level of manganese impurities in the sodium chloride crystal. Vacancy X, chloride. Okay, so we create as many vacancies as we have manganese ions present. Okay, so this is a very effective way in order to introduce defects into crystals. Typically, the number of extrinsic defects is larger than the number of intrinsic defects, unless your crystal is very, very pure. Okay, so even if you do not intentionally introduce these aliovalent impurities, they're often naturally present. Okay, and unless you pay particular attention to producing a very, very pure crystal by excluding impurities, the number of extrinsic defects are larger than the number of intrinsic defects. Okay, so now we have looked at defects in more general. Now let's have a look at what crystal structures are generally favoring ion conductivity. Okay, so a number of rules that we can apply to crystal structures favoring ion conductivity. So they are listed here. So the first one is that a large number of ions, we are meaning cations here, of one species should be mobile. Okay, so this requires a large number of empty sites, either vacancies or accessible interstitial sites. So any crystal structure that basically fulfills that condition will likely be a crystal structure that favors ion conductivity. Okay. So the reason for that is that the empty sites are needed for ions to move through that lattice. Of course, these empty sites can be further enhanced by introducing defects into the crystal structure. So secondly, the empty and the occupied sites should have similar potential energies with a low activation area for jumping between the neighboring sites. Okay, so the reason for that is that high activation area decreases carrier mobility. Okay, and very stable sites with deep potential wells lead to carrier localization. Okay, so if we have two sites that are accessible by the ion, but there's a huge activation barrier in between them. Even though that we have a vacancy present, our ion can actually not easily go into that vacancy because of the huge activation barrier that needs to be overcome. Okay, so the third rule is that the structure should have a solid framework, preferably three-dimensional, permeated by open channels. So a three-dimensional structure is preferable because the ion conductivity can occur multiple ways. Okay, so there are the statistically greatest number of possible paths the ion can actually go through the lattice when we have a three-dimensional framework with three-dimensional open channels. Okay, so ideally one lattice, partial lattice, would be molten, so that the and the other ion would just basically provide the host for the melt. Okay, so we could have practically an anionic framework with the ions being basically fixed on their position, but the cations would be able to move like a liquid through that solid of the anion. Okay, this way basically the anion framework is as the function in order to prevent the entire material from melting and keeping it solid. Okay, so when we talk about cation conductivity, then the anions should be highly polarizable. So this is because when the anions are highly polarizable, they are soft, so that they can deform relatively easily when a cation actually tries to squeeze through an interstitial site, either onto that interstitial site or through that interstitial site to another vacancy. So now let's apply these general rules and look at a number of cation conductors and try to understand why these cation conductors support ion conductivity. So one very interesting ion conductor is alpha silver iodide, which can actually conduct silver ions. Okay, so you see that for this compound, certainly rule number 4 would be fulfilled. We have anions that are highly polarizable. Okay, so iodide ions, just due to their size, are highly polarizable anions. Okay, so now I've told you in the last class that there are two phases of silver iodide. So one is the beta silver iodide, which is a very low ion conductivity, and one is the alpha iodide, which has a very high silver ion conductivity. So you see that rule number 4 is certainly not sufficient to produce a good ion conductor. So both of these phases contain iodide, okay, but one is very conducting while the other one is not. So therefore, further conditions need to be fulfilled in order to produce silver ion conductivity. So this now has to do with the actual crystal structures of the two compounds and how the ions are arranged relative to each other. So in beta silver iodide, there's even another phase known, which is gamma silver iodide, which has a related structure, and these two are actually in chemical equilibrium at room temperature. We have either a Worksite structure or a zinc blende structure. Okay, so the Worksite structure is shown here. Remember, in the Worksite structure, we have a face-centered cubic unit cell with 50% of the tetrahedral holes being filled. Okay, so now the iodide ions, they make the face-centered cubic unit cell, and we have our tetrahedral holes here inside of that unit cell. Okay, but we only need to fill 50% of them. Okay. So now, in principle, you could imagine that a silver ion can actually migrate from an occupied tetrahedral site to another unoccupied tetrahedral site. However, this is not very favorable because these tetrahedra, they are edge sharing, and for that reason we have to overcome a high activation barrier in order to move a silver ion from one side, from an occupied site to an unoccupied site. So therefore the the zinc blende structure and also the Worksite structure are not very supportive for ion conductivity. So in contrast, the alpha silver iodide, which is the high temperature phase, actually at a temperature of 146 degrees Celsius, the beta silver iodide transforms into the alpha silver iodide. And the alpha silver iodide has a different structure. You see the structure here. So in this case, we have a body-centered lattice of silver ions, and you know that the body-centered lattice is somewhat less dense than a cubic or hexagonally packed lattice. So we have here a more open framework of silver ions, and that's the first clue as to why the alpha silver iodide is more ion conducted. However, there's a second point to consider, and that second point is that now the silver ions, they sit on pseudo-tetrahedral holes, of which there are overall 12 within the unit cell, but only 2 of the 12 are actually being occupied. So you see these holes here, and you see that basically they sit on the face of the unit cell, and we have overall 4 of them on each face of the unit cell. Okay, so that gives 4 times 6 is equal to 24. But remember, each phase is being shared with a neighbored unit cell, so for that reason, it's actually on 12 per unit cell. So because of stoichiometry reasons, only 2 of the 12 sites actually need to be occupied. You see one of occupied site here, okay? And you see that now our silver ion is surrounded tetrahedral-like, but actually not exactly tetrahedrally. Okay, so it's surrounded by these 1, 2, 3, 4 iodide ions, but you see that this is not an exactly regular tetrahedron, because that distance here, from here to here, okay, that is a full lattice parameter. Okay, we are going from the body center of this unit cell to the body center of the neighbored unit cell, whereas this distance here, from here to here, and from here to here, okay, is only is half of the body diagonal to the unit cell. Yeah. So the environment is only approximately tetrahedral, but not exactly tetrahedral. More importantly, though, two of these pseudo-tetrahedral are edge sharing. Okay, so this one here shares, for instance, sorry, they are not edge sharing; they are phase sharing with enabled tetrahedral hole. And now, because of that phase sharing nature, the silver ions can very easily go from one tetrahedral hole to enabled tetrahedral hole. Okay, so overall, we have more holes present, and these holes are phase sharing, which further enables the ion migration because the activation barrier is decreased. So the activation barrier in alpha silver iodide is actually only 0.05 electron volts, which is extremely low. Okay. In fact, in alpha iodide, the silver ions are actually so mobile so that we can consider our silver ions to be a molten sublattice within a non-molten iodide lattice. Okay. You can also experimentally support this by doing entropy measurements. So when you go from beta silver iodide to alpha silver iodide and measure the entropy change, then the entropy change is 14.5 joules per mole in Kelvin. Okay. Now, when you fully melt the silver iodide at an even higher temperature, then that increases the entropy further, but only by an amount of 11.3 joules per mole in Kelvin. So this means that this transition here has actually greater entropy increase rather than the melting, full melting of this sodium iodide. Okay, and that's supports the idea that upon this transition here, okay, we are actually really melting this silver sublattice. Okay, and then at higher temperatures, when we fully melt, we also melt the other sublattice. And that's associated with comparable, okay, entropy increases. Okay, you can also see that the sum of these two is similar to the entropy of melting of 1 mole of sodium chloride, which has the same crystal structure. Okay, because of that, we would assume that the entropy change, which is associated with the melting of sodium chloride, will be, sorry, it does not have the same crystal structure, of course. Sodium chloride is sodium chloride crystal structure, but still, despite the crystal structure, the entropies are comparable because the entropies within crystals for different crystal structures actually doesn't vary significantly. Okay, so silver iodide is a really interesting ion conductor. Let us look at another one which is interesting. Which is the beta-alumina. And the beta-alumina is a sodium ion conductor. So beta-alumina is a sodium aluminum oxide. So therefore, beta-alumina is actually a misnomer because alumina would imply the composition Al2O3. Originally, it was actually believed that beta-alumina would only contain aluminum and oxygen, and only after it has been named, it was discovered that it also contains sodium, but the name just remained the same. So beta-alumina was discovered in the 1960s at Ford, and has actually triggered a lot of research on ion conductors in general. How can we understand the ion conductivity in beta-alumina? We can understand this again by looking at the crystal structure, which is shown here. So you have basically an FCC packing of oxygen. Okay, whereby the stacking sequence is some more complicated. So in every fifth layer, 3/4 of the oxygen ions are missing. And overall, we have a sequence of layers which follows the sequence B, A, B, C, A, C, A, C, B, A, and then that's a full repeating unit. Okay. So you see here, we have here these 4 layers in parentheses. Okay. And these 4 layers are fully packed with oxygen ions. And then every fifth one, this P layer and this C layer here, have oxygen ions missing. Okay? So within these 4 layers, which are shown here, because we have more oxygen, we also need oxide ions, we also need more cations. And these cations, which are aluminum and sodium, they are arranged very similar as they are arranged in the spinel structure. Therefore, these 4 layers here, they're also called the spinel block. Okay? But in every fifth layer, we have less many oxide ions. For that reason, we also need less many sodium ions. So therefore, these layers are significantly more porous, okay, requiring less many cations, and these less many cations become more mobile. Okay, so because the missing oxide ions are missing in layers, the conductivity, ion conductivity, also occurs in layers, and we have in this case a so-called 2-dimensional ionic conductor. Whereas in the previous example, in the alpha silver iodide, we had a 3-dimensional ion conductor. All right. Now, one application of the beta-alumina is in batteries, in particular sodium-sulfur batteries, because of the high temperature and chemical stability of the beta-alumina. So sodium-sulfur battery is shown schematically here. So in this battery, we have liquid sodium as the anode and liquid sulfur as the cathode. Okay, so at room temperature, sulfur and sodium are solids. For that reason, that battery can only operate it at a temperature in which all components are liquid, and that is a temperature of approximately 300 degrees Celsius. So in between that liquid sodium and that liquid sulfur, we have a beta-alumina membrane. Of course, the high chemical inertness of that membrane here is very important, obviously, for safety reasons, as if, for instance, that membrane here broke, we would have a direct reaction between liquid sodium and liquid sulfur, which would certainly lead to an explosion of that, that battery. So what would happen at the anode and the cathode respectively? So at the anode, the sodium ions, as the sodium would be oxidized to form sodium plus, okay, and electrons would be produced, and these electrons would move through the cathode, and at the cathode they would reduce the sulfur. In particular, the sulfur would be reduced to S5 2- ions under the conditions. Okay, so overall we would have the reaction sodium plus sulfur giving Na2S5, a sodium sulfide. All right. Now, in order to provide charge balance, the sodium ions would have to move through our beta-alumina and ion pair the S5 2- anions. So this kind of battery is, by the way, reversible. So when you apply a voltage, then you can drive that reaction also into the opposite direction. And in this case, the sodium ions would move into the opposite direction. The advantage of that kind of battery is that it has a quite high energy density of 1040 watt-hours per kilogram, just because it can store so many charges in liquid sodium and liquid sulfur, and it has also a relatively high open circuit voltage of 2 volts. Okay. The battery is also rechargeable with a high charge discharge efficiency, so that means that you can get 90% of the energy which is in the battery, chemical energy which is in the battery, converted into electrical energy upon charge and discharge, respectively. All right, now we have discussed 2 examples of cation conductors. Now let's have a closer look at anion conductors. We said previously there are actually only 2 kinds of anion conductors known: oxide ion conductors and fluoride anion conductors. The reason for that is that these are the smallest anions that we know. So what are the design principles for oxide anion conductors? So similar actually for the cation conductor than those for the cation conductors. So again, you need a high concentration of anion vacancies to make the oxide ion hopping to occur. We'd like to have a high symmetry and ideally a 3-dimensional framework that allows for 3-dimensional ion conduction. And the high symmetry also more likely provides equivalent potentials, energies between the occupied and the vacant sites. So you kind of like to have an open structure with a high specific free volume, which is nothing else but the free volume within the crystal structure and the total volume of the crystal structure. Because the more void spaces you have, the more diffusion pathways for oxygen ions are possible, and the smaller the activation energies. Okay. Again, you would like to have polarizable counter ions. In this case, this would be the cations, because they can easily deform while the anion migrates. Again, that lowers also the activation energy. So of course, you would like to have a favorable chemical stability. If you want to commercialize this, you have to also look at the cost. Thermal expansion is another characteristic in electrochemical devices, because you do not want to have an interrupted ionic circuit because of thermal expansion of your electrode material. Okay, so now what are typical oxide ion conductors? I've already said that previously that the fluoride structure supports anion conductivity. So the fluoride is a fluoride, but there are oxide analogs that also make the fluoride structure. And one example is the zirconium dioxide. So for zirconium dioxide, we know two phases, one room temperature phase and one high temperature phase. So the room temperature phase is denser and is not ionically conducting. In this case, we have 7 coordinated zirconium, and the O2 minus ions are 4 plus 3 coordinated. So they are also overall 7 coordinated. Sorry, this is actually not correct. So some of them are 4 coordinated and some of them are 3 coordinated. Okay, so this gives an average coordination of 3.5. Okay, and that has to be so when the coordination number of zirconium is 7, because we have zirconium dioxide, the number of oxide ions is twice the number of zirconium ions. Therefore, the coordination number of oxide ions must be half than the coordination number of the zirconium ions. Okay, now the anion conductive form of zirconium dioxide is the high temperature form, which has a fluoride structure. And as you remember, in the fluoride structure, we have the zirconium in the the oxide ions in 100% of the tetrahedral sites, tetrahedral holes, as you can see here. So for that reason, now the zirconium is surrounded in a cubic fashion, okay? But only 50% of these cubes are centered with zirconium. The other 50% are just empty, because the fluoride structure can be conceived as a defect cesium chloride structure. So this gives now actually rise to the opportunity of oxide ion migration. Now, however, unfortunately, the high temperature structure is only stable at a temperature above 1000 degrees Celsius, which is not very good for practical applications. Therefore, that zirconium oxide is typically doped, in that doping fulfills 2 purposes. The first one is it stabilizes the high symmetry cubic structure, okay, so that it can exist at lower temperatures. And the second one is that you can introduce additional ion vacancies when you dope the zirconium dioxide with with ions that have a lower valency. Okay? So because of the lower valency of the impurity cations, we need less oxide anions, which creates additional vacancies through which the remaining oxide ions can migrate. Okay, so typical dopants are yttrium. Okay, yttrium 3 plus has 1 valence less than zirconium 4 plus. You can also dope with calcium. Calcium 2 plus is even 2 positive charges less than zirconium. Zirconium 4 plus. Okay. So alternatively, you can also replace zirconium with a larger cation. For instance, cesium 4 plus in order to stabilize the crystal structure. The cesium is larger because the larger size, also the crystal structure becomes more open, and because of that, we are having better ion conductivity. Okay. Another possibility is to dope with bismuth 3 plus. So bismuth 3 plus actually is both larger than zirconium, but it also has a valence less. So in this case, we even increase also the vacancy concentration. So you see the effects of the ions summarized here. So in this case, we have yttrium doping. So yttrium doping of zirconia. So the zirconia 4 plus has a radius of 0.86 angstroms, and the overall free specific volume within that structure is 0.31. Okay, so that means 31% of the space within the structure is not occupied by an anion. And that leads to a conductivity of 0.03 Siemens per centimeters at 800 degrees Celsius. Remember, again, you can achieve anion conductivity only at quite high temperatures. Okay, so now we can compare that to a comparable compound, cerium gadolinium oxide. So here we have basically a cerium dioxide-based ion conductor, which also makes the fluoride structure, but now we dope this one with gadolinium 3 plus. So now all of our cations are larger. Okay, so the cerium is larger. It has a diameter of 1.01 angstroms, which is larger than that of zirconium. Okay, and we also dope with a larger cation. Okay, so that leads to an overall larger free specific volume, and not only the volume fraction is larger, also the pore sizes in between the ions is getting larger. And as a consequence, we are having a higher ion conductivity of 0.15 Siemens per centimeter at 800 degrees Celsius. So here's a third example. We have gamma bismuth oxide Bi2O3. This is also a fluoride-derived structure. So you can consider this as a defect Bi2O4. Okay, and BO2O4 is nothing else but BiO2 times 2, right? So the empirical formula would be BiO2. Okay, but now some of the oxide ions are missing because the bismuth has a 3 plus charge, and the composition becomes Bi2O3. So we have basically a fluoride structure here in which 25% of the oxide sites are not being occupied. right? So bismuth is quite large. It has a diameter, sorry, the radius of 1.17 angstroms. So we have here 25% of the oxide ions missing. So we have a quite high specific free volume. So 50% of the space within the crystal structure is not occupied, and that leads to a quite high ion conductivity of 1.0 Siemens per centimeter at 800 degrees Celsius. Or precisely in this case, only 730. So that sounds wonderful, but there's a catch. Bi2O3 is only cubic from 730 degrees Celsius up to its melting point. Okay, so it's a very narrow temperature range in which you can actually use it as an ion conductor. And doping is necessary to stabilize the crystal structure at lower temperatures. Okay, I see our time is over, so let us stop at this point.